France won. That's just bad news. France won. Yeah, they're playing Belgium. We were in Belgium last year. We liked Belgium.
So
Hey.
this is a long shot.
Yeah?
But so I just, literally just saw Amanda Zoom at work about, I submitted or closed out on my tab on my test.
Oh.
Like 75% of the way through.
Right.
And she's just told me that they have to be turned in by 4 p.m. today, which is
You got 1 minute?
1 minute. And I went home, changed, and now I'm here. So is there any way to extend that?
Sure. We'll extend it for you. How much do you need?
I can get it done when I get done with my class.
Okay, do that. Mm-hmm. So how are things going? You guys surviving this last week? I should be available if you have any questions this week. I should be in my office most of the time. Usually I go run home for lunch to let dogs in and out. But other than that, I should be around. Tomorrow I'm helping with governor's school somehow. There's some kind of Shark Tank thing, so I'll be helping with that somehow. Someone called a favor, and I was like, fine. So I'll be doing that tomorrow morning. And if you just want to set up an appointment by email, if you want to come see me, that'd be perfectly fine. So summer's kind of a crazy time, and this class is so condensed that we're trying to be flexible with you, and hopefully you're flexible with us because of all the crazy stuff that goes on with just summer stuff. So if you have anything and you need help with something, just ask. Being flexible doesn't always mean that we're easy. The material still needs to be covered. I think you guys probably got I want to say they get the raw end of the stick because the first time this class was taught, it was taught by a graduate student, and I think
It was very easy.
it was ridiculously easy, and I don't think that served you guys well, because I think there's a lot of things that are really, really important in this topic, and I think both of us, the first time we taught this class, I think it went really well, but I think that there's things we learned, and I think this time we learned even more about how to. I think the hard part is getting it in 8 weeks, right? Because this is a year-long class, and we're doing it in a quarter of the time, and so anytime that there's any kind of adaptation that needs to happen, it's a pretty big deal, and we recognize that. So anyway, I think there's things that, like this topic, I think I would move to 2 weeks earlier, right after we. This is a really, really important topic in biochem. In biochemistry, and I think some of you guys taken immunology, or do you take immunology next year? Yeah, so this is going to be like a precursor. In fact, some of the slides will be very similar to what you see. Who teaches immunology?
I don't know actually.
It's my mind is so blank. Yeah, I have a grant with it, the R15, or he used to be in biochemistry.
I don't know.
You had a grant with him and Christine.
My grandma.
With
Oh, Glenn Dorson.
Yeah, Glenn Dorson. Glenn Dorson teaches this class. So,
That'll be a fun class.
well, if I could teach 2 classes in this world, biochemistry would be one of them, and immunology would be the other one. Because the topic, I don't know enough about immunology. I'll be completely honest with you. Immunology is one of those subjects that is as complicated as biochemistry, and it changes every single day, like crazy, ridiculous amounts. And so we're going to talk about the very basics of immunology, but I think it's just really important to know that this topic is so vast, and I even, I sit on grant study sections where we talk about this topic, and in a 3-month stretch, things will change really dramatically, to the point that we're like, a grant would get funded or not funded in a 3-month period because of what's changing in the field. So just recognize that there's a lot going on here. So, all right, we'll start with a case study. 12-year-old girl with a history of asthma presents to the emergency department with a 3-day history of increased work of breathing, cough, and wheezing. She reported no clear trigger for respiratory symptoms, although she had noted some symptoms in a mild upper respiratory tract infection. On the day of presentation, the patient awoke feeling suffocated, and her mother noted her lips were blue. In the emergency department, her oxygen saturation was 85%, and her respiratory rate was 40 breaths per minute. She had significantly increased work of breathing and poor air entry bilaterally to both lungs, and wheezing in the upper lung zone. Her chest x-ray showed hyperinflation and no focal findings. What is your diagnosis? Obviously, she has what? Asthma.
I was going to guess cancer.
Yeah, that goes over well with the patient. Sorry, you have cancer. No, wait a minute. Anyone want to venture a guess?
An allergic reaction. I just
No,
saw the
that's-
next slide, so that's
Oh, you looked at the next slide? Oh.
Yeah.
It's supposed to be hidden. So I'm going to tell you a really weird story that happened to me. I used to coach soccer. I think I probably told you guys this. We're at a soccer game. It's July. It's we're out west where it's like a desert, right? And we're playing. It's the second or third game of the day. So it's like 103 outside, right? And these poor kids are out there. I don't know who decided that was a good idea. It's kind of like playing soccer with its 90 degrees and 90% humidity. But we have these kids out there playing. The air's kind of circulating quite a bit. And this girl, I coach girls because I have 2 daughters. And so this girl on my daughter's team that we were coaching waved me off, said, I'm not feeling well. And I said, okay, I'll get you out the next time. And then she comes over the sidelines, I can't wait. And her fingers are getting all big and her face is literally puffing up. And it was insane puff up. And I look over and I look over the rep, I'm like, hey, I need to get her out right now. And so get her out. I'm talking to her. And I was like, just take a break, let's see what happens. I look over 3 minutes later, and she's like, her face is like, I mean, it's enormous. I mean, I was just like, holy cow. So I'm like, we need to call an ambulance right now, figure out what's going on. And I had no idea. I didn't have no idea what was going on, right? Now I would know exactly what was going on, but she was having an anaphylactic shock reaction. And so luckily one of the dads was a trained EMT, and he's like, he found an EpiPen, jabbed her with it, and she wasn't okay. So I called, and I'm going to tell you the story. It has nothing to do with class, but it's kind of a funny story that relates to the topic. So we called called 911. There's like, we're in a soccer field, and like I can see the fire department. Like if I look over, I can see, right? And like literally a mile away is the hospital. Like I can't see the hospital, but frankly, it takes. I said, look, this is where we are. Do not go over to the other side of the complex because that you'll get lost over there. They'll find us. So what do? They immediately go to the other side of the complex and get lost, and they can't find us. So it takes them 10 minutes to get to where we are, and I can literally see them from where I'm standing. Right? It's not like it's like that hard to find. They drive up on the field. At this point, she's literally minutes away from dying. I mean, from anaphylactic shock. And luckily, we got one into her. They ended up putting 7 doses of adrenaline into her to keep her alive that night. 7, you can imagine. You get putting more and more and more to get her to go down. And we had no idea what was causing the problem. What ended up happening was, and this is kind of the weirdest thing, and if you, actually I've seen several discussions of this recently, but she had a protein-induced exercise-mediated anaphylactic shock reaction. So she could not eat meat before she went out and exercised anymore for the rest of her life, because that's what. Yeah, crazy, huh? And it happened one more time to her. She went on to play college soccer, and across her career it happened one more time. So, anyways, there's some really weird things that happen. It was the closest I've had a lot of things happen: broken legs, concussions. This was right up there with the seizure that I had in the middle of the field, where the kid, one of my favorite players, started having a seizure in the middle of the soccer field, and we ended up calling the hospital. But this one takes the cake as far as craziness and near death. So the immune system, this is a case study, right? The immune system can get out of control really fast. Is the point of that story, and it all happens. This is one reaction. All this happens in relation to we get your immune cells get introduced to this allergen. All of a sudden, they get introduced to a mast cell who's going to introduce histamine into the system and other chemicals, and that's just going to keep happening. And it's going to spiral out of control, and eventually, what ends up happening is, this is a normal airway, right? This is a smooth airway in this case study. And you end up with very constricted, or you end up with anaphylactic, which happens all across to your entire body. So this same phenomenon happens everywhere. So today we're going to talk about the immune system. There's 3 different layers to the immune system. You, me, and everybody is in a constant state of attack from viruses, bacteria, small cell organisms. We're constantly under attack. And it's directed, there's several good books out there that talk about this being the single greatest force of evolution that exists, right? And if you look at some of the technology, we'll discuss some of the technology, or some of the genetic editing tomorrow that's occurred because of this. It's some of the most complicated biology that you're ever going to find. We've developed some really simple things like skin, mucous membranes, and secretions to fight. That's kind of like our first line of defense. We have a second line of defense where we have phagocytic white cells. We have antimicrobial proteins, and we have an inflammatory response. Those are kind of like the second line. And then we've even developed a third line of defense where we have antibodies and lymphocytes. And this is what we're going to talk about today, primarily. We're going to talk about all of these different things and how they interact. And tomorrow we'll talk about vaccines and antibodies as therapeutics, and then we'll also dive into some of the sensory cells. So today, here's kind of a graphic that shows how this works. So first line is our skin and mucous membranes. These kind of prevent just the general attack. This is why getting a cut or a burn is kind of a big deal, right? Because they're the first line. If you don't have that going on, and this is also why when you get, an infection, sinus infection, or viral infection, this is why you get stuffed up, right? Your mucus goes crazy. It's a line of defense to prevent against these kind of infections. Second line, obviously we have these cells that come in. They can attack. They attack certain types of infections. This is a bacterial infection. These are helminths or worms. Other kind of infections get through, and then that leaves for our third line of defense, which are lymphocytes, and some of our T cells, and then we also have antibodies. So those are the three major lines of, and we're going to talk in detail about all of them, and we'll talk about them from a biochemical perspective, not our biochemistry perspective, not necessarily in detail, but just enough to give you an exposure, because we've spent a lot of time this semester building a foundation, and I think that's an important aspect of what we kind of just give a description of how this works. So skin is the first and most important. We have multiple layers. In between these layers, the skins have developed what's called a tight junction, this TJ. And if you look at and you kind of explode a tight junction, this is what you'd see. We have claudins and we have other proteins, occludins, that kind of keep the cells locked together so things can't penetrate. So develop these tight junctions that prevent things from filtering through and getting through to the next layer, right? It's also important that we have, we need to get stuff through there, right? You can actually administer stuff through skin. We've developed microneedles and other kinds of big needles to penetrate this dermis so we can get stuff into the skin and through the skin to deliver it as a vaccine or therapeutics, right? There's tons of people who take patches, and, right? We can get stuff through there. But we've developed, this is the first line, these claudins and other proteins that kind of strengthen, and we have multiple layers, and then we have these tight junctions that form that allow things, prevent things from going through. So that's the first, probably the most important line of defense. We also have mucus and cilia, are if you get stuff caught in your lungs, there's cilia along your trachea and other parts of the pulmonary system, and they're going to sweep particulates and other things up through and out. As we cough up phlegm and stuff, that's kind of what you're doing. And these are basically, anyone want to guess what those are? Those cilia are? Good guess. They're like tiny hairs. They're proteoglycans. So remember when we talked about carbohydrates? That's what these are right here. Which is proteoglycans. They're cilia, and they just kind of flow the particulates up and out. Tiny hairs basically the effect of what they are, but from a biochemistry, what is your hair? What is your hair made of? It's keratin, which is what? It's a protein. So these are very similar, but these are proteins that have what? What is a proteoglycan? I know I'm stretching you a little bit. You can spit it out. Don't be afraid to guess. No, I won't mock you or anything. Just a guess. What are your choices? Is it DNA? Does anyone know any time that we use DNA outside of transmitting information? Lipids. Lipids? Yeah.
I'm voting for
You're voting for lipids. Got it. Got it. So we got a lipid vote. Anyone else want to vote lipids? Or is he going to be on an island? What's the last choice that it could be? We know it's already. I already told you it's protein. Some protein. What's the other biomarker molecule that we have? You really like it. Tastes really good. Yep, carbohydrates. So is it a lipid or is it carbohydrate? Can you change your vote? Change your vote. These are big sugar structures, right? So they're big carbohydrates. So this is a protein carbohydrate structure, and they sweep the particulate out, and we excrete mucus. Anyone want to guess what mucus is? Huh? No, well, that's what gets caught in mucus, right? So there is bacteria in mucus. There are bacteria and viruses. Yeah, that is true, but we don't actually put them in there, right? When we make the mucus, like you make mucus, right? So what do you think it is? What are your 4 choices? Okay, lipid. Anyone else want to vote with lipid? I'll give you a hint. It's similar to the last one. It's a carbohydrate. Yeah, you don't realize how important all these things really are until you start seeing the different applications that we, as multicellular organisms, we've adapted to use these different things in different ways. So this is so mucus is actually a glycoprotein too, and they have a very, very high carbohydrate content. They're very polydisperse, so there's a large amount of variation. A lot of them are sulfated, and so they're charged, and that attracts things in. And so all this kind of stuff, and they also have a lot of sialic acid. So this is how your body has adapted to deal with these kind of things as one of the first lines of mechanism. Second, again, also in the first line is sweat. Sweat has a lot of salt. Okay, high salt content. It has lysozymes, which is what? What is that? If you had to guess what a lysozyme was, what would you guess? An enzyme? You'd be right, right? So it degrades peptidoglycan. What are enzymes made out of? Proteins, right? Proteins. We got peroxidase enzymes. They decompose H2O2. What other peroxidase enzymes have we discussed in class? SOD1. Do you remember what SOD1 does? It is, yes. It's for degenerative myelopathy. What other human disease is associated with that?
MS.
S is right.
Yeah, MS is right.
MS or ALS, right?
Yeah.
Lou Gehrig's disease. What is it? Alateral. My mind is going blank on ALS. I was just called Lou Gehrig's disease. Anyway, so ALS is the disease that also has associated peroxidases. This actually decomposes H2O2. Lactoferrin binds iron. Bacteria. What do we know about why is iron important? Why are these metals important? Where have we seen all these things showing up? Yeah, we have there. Where else? They're cofactors for all kinds of things, right? Where else do we see iron that's really important? It's not necessarily a cofactor, but a binding agent. Heme, right? So I'm just going to tell you that if you attack the ability of a bacteria or other microbes to uptake iron or other metals, you are significantly hampering their ability to function. And this is one of the main reasons why. Okay? A lot of enzymes, cofactors, they also use it for binding oxygen, all kinds of things like that. So this lactoferrin is actually a very large protein that binds iron. What do you think the prosthetic group in there is? Give you a hint. It's related to hemoglobin. What binds hemoglobin? What binds inside hemoglobin? In the name. Heme, right? Yeah, so there's also certain groups that are associated with that. Defensins, they form pores. They're a protein that forms pores inside the microbial. Well, why is forming a pore a bad thing? Yeah, so what do we use membranes for? Yes, what do we keep in? The good stuff, nutrients, right? We keep in all the ability for the metabolites, right? Your NAD plus, all of your cofactors that we just talked about. There's tons of things we keep in, right? What do we have across the membrane? Yeah, like what?
Water stuff?
Chemical gradients, electrical gradients, right? For generating, right? Right? If I create a pore and a bunch of sodium goes in, or is that going to change the electrical composition? Absolutely. It's going to change the electrical composition, going to metabolize things. So, as a defensive forms a pore, that pore is a big deal for that bacteria, right? Because all of a sudden we got stuff going in and out that shouldn't go in and out, because that's what we use the membranes for. Also, we have acids, so we have low pH in sweat, and that allows, and even in the stomach, right, which is also an important, right, because you're going to eat stuff, right? You eat bacteria, E. coli that you shouldn't, viruses that you shouldn't. That low pH in the stomach is going to denature a whole bunch of, and kill a whole bunch of things. So those are the sweat and stomach. Those are also antimicrobial barriers. So that's the first line of defense. And that's the general biochemistry. There's a lot of biochemistry associated with that. Second line of defense, white blood cells is the first one. So if you actually get past the first line of defense, you're going to get to white blood cells. And they circulate through, and they're going to phagocytose, right? Anyone know what phagocytosis is? They're going to eat things, right? Yes, they're going to, and that's kind of what you see here, right? You get these, there's a bacteria there, and we've got these, we're going to try to endocytose that bacteria. How we do that, bacteria adheres to the phagocyte, and engulfs it. Then in that vesicle, right, what's going to happen is we're going to pump in a bunch of, we're going to lower the pH, right? And we're probably going to pump in a whole bunch of other things in that. And that's going to cause the cell to lyse. And then that lysis, right, we're going to have a residual body in there after it gets digested and killed with all kinds of, basically with acid and hydrolases and other enzymes. And then we're going to put it back out into the environment as a mixture. Why do we do that? Okay, we do need to get rid of it, right? This will come back, so just make a mental note. This is one of the things that we do. We don't just put it back in and never see it again. The second line of defense also includes an inflammatory response, and you're probably all really familiar with this. And inflammation is a pretty significant problem. I think it's a mosquito bite. Right? We've all had that. Sometimes you get a mosquito bite and it turns into an enormous big red mass, or if you sprain your ankle, right? Bee sting, any number of things. Inflammation is a line of defense. So your capillaries dilate, you get pyrogens, there's pain receptors that are activated, that's why it's so painful. White blood cells are going to flock, there's all kinds of cytokines in that. So is inflammation a good thing or a bad thing? Both. Exactly right. It is good, it does fight off things, but it can get out of control. That's the thing that I want you to remember the most about the immune system. The immune system is neither good nor bad. It does good a lot. It can also do a lot of bad things, and we'll talk about the bad things at the end of the lecture. Here's kind of a graphic representation. So you have some kind of, say, splinter, and the pathogens are associated with that. There's chemical signals that are sent, right? Histamine and prostaglandins are released. From there, we're going to, if there's a red blood cell, we're going to have our capillaries are going to dilate. We're also going to have clotting that's formed, so you're going to get a clot that's formed in there eventually. And then you're going to have white blood cells are going to start coming through the blood or lymph, and they're going to start phagocytosing all of those pathogens, debris. Well, that makes it big and red and inflamed, right? Sorry to use the word to describe the word, but it becomes very, very tender, very red because there's a lot of blood vessels, and dilated.
Can you go back to that slide?
Sure.
So from our discussion yesterday, guys, from our questions that we did, how does aspirin work? Where's the intervening? Yeah, so you're decreasing inflammation, but what enzyme is doing that? What's aspirin interacting with that's doing that?
It's like oxomes
Cyclo.
Prostaglandin dehydrogenase, right? And then cyclooxygenase. So it interacts with both of those. So if you're hitting right in that first step, you don't proceed all the way through. So when you're using aspirin to decrease inflammation, you're actually inhibiting that very first step. And that's how you're controlling inflammation. Thanks.
So could taking aspirin potentially make things worse?
Absolutely. How could it make things worse?
You don't fight it off right away, it's just gonna spread.
Yeah. So think about it this way. If you have a fever, how many of you guys are like, man, I feel horrible, I've got this fever, I'm going to take something right away? How many of you take something right away for a fever? Yeah? So based on this and what we just learned about the immune system, should you take something right away for a fever? You don't think so? Why not actually? Yeah, so it's one of those things that, like Ben was talking about, it can go really, really good until the point when it's not. And so, and I'm not saying that it's right or wrong to take something right away for a fever. Just recognize that that's what you're doing, is you're controlling the inflammatory process, and the inflammatory process is actually a part of your immune response. So it's part of your body's way of fighting things off. Our kids kind of hate that we're biochemists because when they were younger, they would be like, oh, I feel so sick. We're like, stick it out because you're going to be stronger after.
It's true.
So, of course, we did have a whiner, so
That's true.
that's fair.
How many of you guys watch House?
It's never lupus.
It's
It's never lupus.
well, but like in about half the episodes of House, right? House is he's a diagnostician basically. So his specialty is finding out the tough cases that no one else can figure out. In about half the cases, it's either they either have to give steroids or antibiotics or whatever, right? If they give one, then the other one. This is the scenario, right? So if you decrease the immune response, that's what a steroid would do. Or you give antibiotics, you're going to kill the infection. So this is the trade-off that always exists. Oh, I shouldn't say always, but 9 times out of 10, like House is fighting that battle, right, between that, because it makes for a compelling story. This trade-off that exists. If you give steroids, you're going to kill with infection. If it's wrong, if you give them antibiotics, then it's an inflammation response. It could kill them because the inflammation is going to take off. So you're going to increase the inflammation. So that's the trade-off that you're going to see. You may see this.
This isn't actually far from the truth. If you notice in a lot of your commercials for chemotherapeutics and for some of these like Humira and things, have you guys ever listened to the contraindications and some of the side effects? What's one of the number one side effects that they say?
Diarrhea.
That's
Sorry.
Decreased immune system.
decreased immune response. because you're suppressing the inflammatory response.
Tuberculosis, right? They always are like
Tuberculosis.
is the number one always that they say.
Yeah, because
Besides diarrhea,
tuberculosis
of course.
will hang out and become very quiescent, so you don't know you have it, and then when you suppress the immune system, it flares up. Shingles will do the same thing. So that's why when you're dispensing drugs as pharmacists, you have to know that patient's history. Because if they've been exposed to something like that in the past, that may be an important item to counsel about with that particular patient, is keep in mind that this is going to suppress your immune system perhaps. Anyway, just a couple connections there for you.
Yeah. I wish if I could do it all over again, immunology would be one of the things that I might actually go become a doctor. Now, I'm not saying I'd be a doctor, but I mean, who really wants to be a doctor? But
Not an MD.
not an MD anyway, right? All right. So, second line of defense, interferon, right? I wouldn't go that low, is what I'm saying. It's a lowly station is to be a doctor. MD is just a clinician. The reason we're so snotty is because they're so snotty to us all the time, right? I interact with MDs all the time in my research, and they're always like, "Well, let me tell you how," and you're like, "F you," right? Let me tell you how it works, right? So anyway.
How it happens between pharmacists and doctors every once in a
It
while.
does.
It does. Yeah,
Okay.
they're like, oh, you just have a farm bee.
I don't know what you're talking about.
Anyway, sorry, I didn't mean to reject that. Second line of defense, interferon. So if a virus infects your cell, right, it's going to come in and you're going to get, what ends up basically happening is the cell changes and it's hijacked. All of the transcription, replication, all that kind of machinery is hijacked, and in that process, more viruses are made, right? So the virus hijacks that cell and new viruses are being made. Well, the infected cell makes interferon, right? And that's kind of secreted out in the general area, right? That secretion allows other cells to make and stimulate antiviral proteins which block viral reproduction. So we've actually developed a mechanism inside of our normal cells to block viral fusion and viral takeover of our cells. So that's interferon. So that's another virus-mediated chemical that our cells as a second line of defense. Okay, so that's the second line of defense. Now we'll talk about the third line of defense. Third line of defense is probably the most complicated, most sophisticated, and it's the most long-lasting. The difference between this line and the other lines is generally it's very specific. So the first and second lines are very generic. They'll stop any kind of attack that comes along. We haven't talked about complement, since complement is mediated by antibodies commonly. We'll talk about that a little later. But the third line of defense is antibodies. It's very specific. Okay? So it's looking at specific hosts, specific microbes, specific antigens. And so it's actually, does everyone know what an antigen is? Did I just get ahead of myself?
I think we've talked about antigens in the past.
Antigen is a foreign entity. It can be, usually it's biological, but it doesn't necessarily have to be. Generally they're proteins, but it can also be carbohydrates and DNA and other biomolecules. So an antigen is just a foreign entity. So there's two major types. Right here is antibodies. These are B cell mediated, and this is a T cell. And we'll talk about each one of those in a little bit of detail. So the adaptive immune system. So you'll also hear the first two lines are the innate immune system, and the third is the adaptive immune system. So it's adaptive to the host. So those first two lines are commonly referred to as the innate. The adaptive immune system is composed of a humoral response, which is generally antibodies, and it also is mediated by some T cells, CD4 positive T cells, and then we also have cytotoxic T cells. That's referred to as the cellular response, and we'll talk about each one of these and how they influence. So I don't know how many of you guys know this, but I study herpes virus, and we have discussions all the time about how to develop a herpes vaccine that will interface with all of these different mechanisms. And I will just tell you, okay, that we are nowhere for developing some vaccines for some of these viruses. It's like herpes, way smarter than we are. Way smarter than we are. It has 13 glycoproteins. It knows how to block the innate immune system. So we've had one of those glycoproteins blocks complement. Complement is how we normally get rid of certain, I'll talk about complement in a minute. One of them blocks complement. One of them blocks the FC part of an antibody. So it blocks the ability for antibodies to bind to it. And there's 6 or so glycoproteins. We have no idea what they do. They could do all kinds of different stuff in the immune system. So we're fighting a war, and all of, like the grant proposals that I review, a lot of them only cover B cells. We're only talking about the humoral response. I want to know what antibodies are made. We're not even discussing in that grant application how the T cells respond. Or I see grants that have T cells, and they're not even discussing how the B cell response is. And this response is really important, because if I go down one path and I focus on one path, that happens a lot. Maybe tomorrow I'll tell you about leprosy. Because leprosy, depending on which part of the immune system response, can be obviously very toxic. And the other ones, no big deal, you're fine. That's why not everyone gets leprosy. Because your immune system, depending on which side responds, that's how you will, either it'll be toxic to you or not toxic to you. And that could be a matter of just chance, right? A B cell got there before a T cell did, or a T cell there got there before a B cell. When we're still responding to a generic response in vaccine designs, and vaccines will be an important part of what you guys do. In fact, the other day I went to Costco, right? And I was talking to the pharmacist, right? And I was like, hey, I want the shingles vaccine because I really don't want shingles. Like, well, you have to be 50. And I was like, why? Do I have to be 50? Otherwise, you have to pay for it. And I was like, I'm close to 50. I don't know what that cutoff is, but I know people my age have gotten shingles, and I don't want shingles. And I hadn't had the discussion with her, like, I know that there's people who are my age that have shingles, and I don't know. So, you'll have that discussion with your patients as far as.
Did you just get your doctor to write a script over there?
I need to. I know, I need to. I haven't yet.
I don't know why they do that.
I don't either.
Can you contract shingles from like another person even if you've never had chickenpox before?
It's a great question, and the answer to the question is probably.
Because we had a coworker come in with shingles, like didn't realize she had shingles, and then everyone's freaking out, like, can we get it?
I would say the probability is low, but because you already have been exposed, right? And varicella is probably just latent. When you get a shingles exposure, it's likely because it went latent, and then your immune system responded poorly, or you didn't get enough sleep, or you didn't get enough to eat of the right kind, or whatever. And varicella is a herpes virus. It can go latent in your cells, and then it pops back up. That's what happens. It just sits in your cells for 40 years, and all of a sudden it's like popping out because you can get enough sleep on that or something. Yes, that's exactly how I responded to it. Now, does that mean you can get it from your coworkers? Probably not, but I wouldn't put it beyond the realm of possibility. I'll just tell you that. I just would not put it.
I think the dogma says that shingles is non-transmissible. That's the dogma. It doesn't necessarily mean that's always the
I wouldn't be hugging them, let's just put it that way.
You have to it has to be like contact, right, in order to get that.
In theory, sure. Yeah. Viruses are very sneaky. Anytime I see a virus thing that someone says, oh, you can't get this from that, I'm like, hey, I'm not taking that chance. So, Anyway, so we have two responses: humoral, cellular. So let's talk about the humoral, or cellular. Cellular meaning T cells. Okay, so there's three types of T cells: helper T cells, cytotoxic T cells, and T regulatory cells. And T cells are really one of the main functions of T cells is to clean out cells that are dying or having trouble. So T cell therapy, you guys are going to see this, and they've just instituted more. They've just approved more, and they've just instituted more clinical trials on T cell therapies for cancer in particular. And we're actually doing a lot of work as a biomedical engineering community in this area. It's one of the most promising areas that exists. So cytotoxic T cells have antigen receptors, and they bind to protein fragments, and they're going to kill cells. Helper T cells, so cytotoxic T cells are often referred to as a TC, and they have CD8. They're often referred to as CD8 positive cells. Helper T cells are CD4 positive, and they're referred to as TH commonly, and there's multiple different kinds of TH cells. And then these are referred to, T regulatory cells are called Treg, and commonly there's a receptor CD25 on them, although they also do have CD4 on them as well. They modulate, Reg cells modulate the immune system, so their main job is to prevent autoimmune diseases. So they're immunosuppressive, and they downregulate some of the other effector T cells. So they can be. We won't talk more about that, but that's a pretty important area in the whole scope of things.
Hey, Glenn,
Yeah,
do you know if Truvada Prep interacts with T cells?
I don't know the answer to that.
Do any of you guys know from working in pharmacies?
I've
So,
just seen like a bunch of commercials and stuff about it.
yeah,
I tried looking stuff up about it.
the mechanism of action is not clear at all.
What does it say?
It just says it prevents HIV from replicating as it enters the body. So it's an HIV prophylactic, is essentially what they're using it for.
Oh, okay.
But I was just curious if it's interacting with your T cells.
I don't know the answer to that question. I haven't kept up on anything HIV related, so I don't know.
Just curious.
Again, so we're going to talk about cytotoxic T cells. Cytotoxic T cells basically they mature in the thymus. They're involved in cell-mediated immunity. They're activated when a cell presents an antigen, specific antigens to them. So you can have helper T cells, suppressor T cells, memory T cells. There's other kinds of cells that can institute action with them. They basically are cancer cells, are cells that are infected with a virus. This is the kind of thing that will occur. And basically what you're going to have is you're going to have porphyrins that are going to create pores and basically kill that cell. That's the effect. That's that perforin molecule is going to form pores. And so right there you end up with these pores, and that obviously we talked about what pores do to cells, and we are basically killing our own cells because they are cancerous or they're virus infected. Helper T cells, they play an important role in the immune system. They activate other immune cells by releasing cytokines. So if they bind here, they're going to release cytokines that allow them to recruit, or they either regulate immune responses by upregulating it, or they can suppress it as well. So they're also important in making antibodies. So, and we'll talk about that a little bit more later. And they're really, really important and helpful in maximizing the activity of phagocytes like macrophages. We haven't talked about, I didn't go into all the details of the cells that are associated with phagocytosis, but there's a lot. Natural killer cells, macrophages, natural killer cells,
More about each
foreign binding giant cells. There's a whole list of them. That's not really biochemistry per se. That's more immunology. But
We'll get that next
Huh?
time.
yeah. But T helper cells basically are involved, and they upregulate those kind of cells to. So here's a macrophage. It's interfacing. We have a bacteria. We have bacteria antigens that are presented out of. So bacteria get endocytosed into a lysozyme or lysosome, and then antigens are generated. Those antigens are transferred to those. Then T helper cells will present those antigens to B cells, and those B cell presentations allow the body to make antibodies. So this is one of the, and we'll talk about that here more in a minute. So there's a T cell receptor on all of these, right? So this is CD4, and there's a receptor that's associated with that allows the interleukin gets transferred between. So this kind of gives a synopsis of how the B cell can work. So again, you have your macrophage eats a bacteria, right? Interleukin 1 is transferred. The fragments of these proteins, these antigen fragments, are presented, right? We've got, then from there, the T cell can activate B cells, which B cells then make, and we'll talk about this more in a minute, the B cells make antibodies. So now all of a sudden your body's making antibodies. It can also help with the cytotoxic T cells, which we just talked about, where you get attacked on infected cells. There's 4 steps in this process. The first step is phagocytosis. The second step is this recognition step, right here, where we have recognition of what's going between the T helper cell and the macrophage. And we do have what are called professional antigen presenting cells, or APCs. Again, and they're going to endocytose bacteria and viruses. Again, macrophages are the most common. Then we have, and our third step is a verification step, where your TCR, which is this response right here, or this protein right there, validates and then starts to send the signal out. And then the fourth step in the process is proliferation, which is sending out a signal, right? IL-2 and other cytokines to these other responses. Again, T helper cells play an important part in sending the signal to cytotoxic, or the TC, CD8 positive. So these are presented, these antigens are presented, so that then the cytotoxic T cells can then recognize what's going on, and then they will send the perforin in, right? So this antigen was presented to the T helper cell. It activates, it's activated on that receptor. Then the next time it sees that, right, the cytotoxic T cell sees that, it's going to recognize an infected cell, and then it's going to send its perforin to create pores. Ions of water flow in, the bacteria explodes, and from there, that cell is killed. This kind of also shows how, well, there's 2 pathways. We have a T cell dependent antigens and T cell independent. This is a T cell dependent antigens, and this is where we trigger humoral response. Humoral response meaning antibodies, and that requires the help of a T cell, and a T cell will present this to a B cell. So this first part is what we just discussed, and then IL-2 and other cytokines are activated. From there we have a B cell, we have an activated T helper cell. That activated T helper cell will present the antigen that it just received from the macrophage to a B cell, and then the B cell is going to make antibodies, and these are just going to activate clones of the memory B cells, and then those clones of the memory B cells are going to secrete antibodies. So now you have a ton of antibodies that are going in on your cells. So T cells can help initiate the ability for us to make antibodies. We also don't need T cells, so B cells can activate on their own. So B cells have receptors on their surface that are basically antibodies that are bound into the surface, and if they notice that there's a pathogenic entity, it can bind that, and then this and this B cell gets activated, and it starts replicating, and then it'll start secreting antibodies into your bloodstream and into your lymph. So there's two ways of activating cytokine or activating B cells. Antigens also can initiate complement, and this is where complement. So if an antibody binds to a antigen, that could be on a cell surface. Complement proteins can bind to this is the Fc region of the antibody, and then this complex forms. And once this complex forms, it then also can form a pore, and that pore can, obviously pores are very important in killing things, and so that's associated with antibodies as well. So that's part of the humoral response. You guys want a break? Yeah? Okay. Let's give 5-10 minutes. Let's come back at 5. I think maybe I should actually. Well, something else I'll find out. Or anywhere else. Okay, sounds good.
See you later.
Hey.
Hey Ben,
What's up?
did we happen to get that trailer?
I think Amanda did. Why?
Oh, I just wondering if it or not.
Yeah, I'll double check with Amanda. So.
Alright,
Okay. We'll check in tonight. So we'll check in tonight and see what else. Okay. Touch you later. Thanks. Bye. All right, so let's start back up. So, T helper cells can go 3 different pathways. And you'll hear, and we actually know how to control a lot of them through adjuvants. You've probably heard a lot about adjuvants from all the crazy people who talk about anti-vaccination strategies. And I say crazy people, and I literally mean crazy people. Because I'm not discounting the fact that vaccines are perfect, because they're not. Okay? They're absolutely not perfect. But if you want to know on the scale of things, and I'll talk about this tomorrow, the scale of things that have saved most life on this planet, vaccines are number 2. Right? They've saved more people on this planet than everything except for, you want to venture a guess? Nope. Antibiotics are number 3. It's a good guess though, obviously. Clean water. Right? Clean water saves more people than vaccines, but vaccines have saved hundreds of millions of people. So, when we talk about vaccines, we've been doing this a long time. We know a lot about them. We have a friend who did their postdoc or did their graduate work at the Mayo, and she went on to GSK, and she studied adjuvants. Adjuvants are what you put into a vaccine to initiate the immune system to do what it needs to do. You might have heard some of these things before. But CPG and alum are very, very common ones. We know how to initiate all 3 of these responses based on what we inject with our vaccines. We have libraries of molecules that we use that we can initiate a response. So what you have is you have an undifferentiated T helper cell. Okay? Helper cells do what? What does a cytotoxic T cell do? Actually, the helper cell is what activates a B cell. I like the guess. Okay, a cytotoxic, or commonly referred to as a TC cell, it actually is CD8 positive. It's going to go kill the cells by peripherin, right? It's going to form pores. So a cytotoxic T cell actually kills a cell. A T helper cell is going to recruit. Remember, helper will recruit people to do it. Okay, and these are the mechanisms by which it does that. It does that by cytokines. So you see all of these. This is actually really important for you to know, because I'm just going to tell you that all of these cytokines are drug targets. All right, just so you know, because they're anti-inflammatory. So you'll see these. I can tell you that, and these are all really like tiny molecules, and so they're really challenging. Like I tried to develop an antibody against IL-4 imatinib for a long time. It's just really impossible to develop it. I mean, it's not impossible. People do it, but it's really challenging. I'll just say that. So that's why it's important to you. T helper cells, right? You have an undifferentiated T helper cell floating around. T helper cells recruit other cells to help if there's an infection. IFN gamma, IL-12 will cause it to form a Th1 response. Okay, we know how, if we make a vaccine, we can initiate a Th1 response depending on the adjuvant we put in. So if we wanted to make a bacteria against virus, or a vaccine against intracellular bacteria or viruses, we know we want to initiate a Th1 response, right? Which will activate macrophages, CD8 cells, and B cells. CD8 T cells are cytotoxic T cells. That's what causes the porphyrin that causes pores. Okay, so we know that if we have an IFN gamma or IL-12 response, it will differentiate into a Th1. That's going to be effective against, and that's going to call macrophages, CD8 positive T cells and B cells, and that's going to be very effective against bacteria and viruses. If we have large worms, right? Yeah, there's nothing more gross than worms. I'm just going to say that right up front. Like, our dogs got worms, and I was like mortified. I was like, holy cow, that is the most disgusting thing I've ever seen in my entire life. Okay, so if you get worms,
Wait, see it?
oh yeah, their poop comes out, and it's all wormy. Yeah, it's really disgusting. I mean,
all puppies with them.
all puppies get worms. Yes. So you have to. There's nothing worse than seeing your adult dogs, and you're like, oh my word. Anyway, Th0. If I want to get a response against, if I want to generate a response against large worms, I know that I'm going to have to initiate to a Th2 helper cell. That can be initiated by IL-4, IL-5, and IL-13. They're going to be effective against. They're going to generate eosinophils, which are a form of cells of phagocytose, and we're also going to generate B cells. Okay. Th17. Don't ask me why it's Th17. I should actually know that, but I don't know why. Every time I see this, I'm like, why the hell did someone name that Th17? You know, as opposed to Th3, which would be the next logical number, instead of going all the way to Th17. Don't have an idea. IL-7, maybe it's because IL-17, but so IL-17 and IL-22 initiated a Th17. That will generate neutrophils and B cells, and that's effective against some extracellular bacteria and some fungi. Fungi being things like, what are fungi? I'm not talking about mushrooms. What are the fungi that affect? Yeah. You're talking about dogs? Yes, and you can get them too. You can get worms all kinds of different ways. Up through your heels. You can eat food. I mean, you know, yes, because they are very. They're not very big. The eggs and the transmission, the larvae are not very big. Yeah, they're a larvae, and then they'll form into mature, and they'll be in. And they form in different parts of your body. There's heartworm, there's ringworm, there's hookworm. If you go to a third world country, that's probably your number one threat. Your number one threat is worms. We have a very clean environment around here. We're not running around with, they mainly come from poor hygiene. It's a great question. I would encourage you to look up the news, because there's some people go to third world countries and they come back and they're not feeling well, and it's because of a worm infection. I mean, it's just something you have to be concerned about if you're going to travel. That's true, right? So.
Is that related to ringworm at all?
Yeah, exactly. They're all. Yep. Isn't it? I thought it was.
No, it's just like a thing.
Oh, I'm sorry. You're right. That's right. Yeah. Sorry. Yes.
But there's a ton of little worms out there that exist that can cause problems. So we have to give our dogs all kinds of worming medication all the time because of it. We generally have good hygiene in the United States, and so we don't really have to face these problems. It's one of the reasons why I don't know a lot about them per se, but they're a very, very common problem in places where you have poor drinking water, poor sanitation. So we have a different problem in the first world. We are too hygienic. I told you that the immune system is neither good nor bad, right? You probably have moms who are super sterile, super clean, right? That's a good thing to a point, but you need to be exposed to certain antigens in your life. Otherwise, what happens? Your immune system is like, yes, exactly. Your immune system is going to fight something. Okay? Your immune system is going to fight something.
Isn't that why a lot of kids get asthma?
Yes, exactly. It's because they live in a super sterile environment, and guess what? Anything that is super clean, like I don't wash my hands as much as I should, as people say I should. And I'll tell the reason I don't is because I'm just kind of like, hey, you know what? I grew up eating dirt, right? When I was a kid, we just ran around and we did all kinds of crap, right? In the middle of the wilderness, my mom didn't micromanage us. Our kids grew up playing with insecticides, hand wash, probably like you guys did, right? You probably had antimicrobial stuff all the time. You're wiping your hands off, blah, blah. There's a problem with that. You end up with peanut allergies because you weren't exposed to peanuts. You end up with allergies because you weren't exposed to certain antigens. I'm not saying you should let your kids run around playing in the sewer, right? That's not what I'm saying, right? But there is a balance between you can be too clean. You can be too clean. Not in a hospital environment, right? Don't get me wrong. But your kids, I wouldn't be too worried about. Your kids are going to be just fine if they go play in the dirt. In fact, they'll be better off for it because they're not going to get hookworm or anything like that, but they're going to be exposed to different antigens that are not going to be a big deal. So, all right. Okay, so here's kind of a different way of representing that whole thing. They also can do, if they get TGF beta or retinoic acid, it can deactivate and limit our immune response. So we have all these different opportunities for T helper cells to help out, and you can get all kinds of different responses based on the signals that are generated at the site, wherever that is. That can be all throughout your body. Now, one of the important things that happens is B cell activation. The main reason to activate B cells is to secrete antibodies that are going to bind to that organism or threat or molecule or that antigen, and it's hopefully going to neutralize their biological activity. That's the goal. Hopefully, so when let's say we get a large worm infection, you get antigen presentation to the CD4 cells, the CD4 T helper cell. That's going to activate that. Hopefully, it activates B cells. And what are B cells going to do? What are they going to make? Antibodies. If we have a CD8 positive T cells, what do we have? Cytotoxic T cells, which are pore forming, and they're going to try to kill that cell. We actually want to have B cell activation. Again, it's based on all molecular interactions, and it's all based on cytokines. And they're upregulating. These cytokines are secreted all throughout the whole process, and you've got a binding event that occurs between an activated APC and a T helper cell. It's going to have a signal, which is going to be IL-4, and you're going to then differentiate Th2, which then, right, and you're going to have effector cells, these are your proliferation differentiation cells. That's going to initiate B cell plasma, and B cells and plasma cells, and that's going to generate a specific immune response that will be hopefully very specific, right? Because that's what we talked about adaptive immune system being very specific to that. And that's all based on signal of 3 cytokines that occur at the various stages of this process. So all the way through, we have specific cytokines that occur. So acquired immunity, we've kind of hijacked it, which is a good thing, because we want to use this for our own benefit, right? So naturally acquired, if you get an infection, you're going to present that in the antigen, you're going to affect that pathogen, you're going to present that pathogen to your immune system and will generate a response. When mothers, so that's active, right? I'm going to present that, that's going to be active in your body. I can do it passively because I can pass through mother's milk. One of the really important things for breastfeeding, like we don't let our puppies go out into the world when they stop breastfeeding. So around 5 or 6 weeks, puppies stop breastfeeding. And if we haven't given them their immunizations, we don't want them to go out because there's a window there by which the antibodies that are passed from the mother's milk to, and this goes true for your babies as well, right? Human babies. If there's a lot of antibodies that are passed from the mother to the milk, also from the mother via the placenta, the fetus. So they can prevent infections that way. We also can do it artificially. So if we artificially can acquire immunity from vaccine or attenuated pathogens, or we can do it passive. We can do passive immunizations, and I'll do passive. We do passive immunizations. So for herpes, right? We infect guinea pigs because guinea pigs have a reproductive system that is not only inexpensive, but it's comparable to humans as far as herpes goes. So we will take and we do what's called passive immunizations, where we take antibodies that we know are effective against herpes, and we'll inject those antibodies into guinea pigs to see how effective they are preventing the guinea pig from getting the infection. And quite a few of them do a really good job. So in theory, if we wanted to, we could probably do the same thing as humans, although humans are much more complex. So we just presented a paper on this topic that was just accepted a while back on passive immunization. So that's something that we do on a regular basis. And commonly, these can be used as therapeutics. We just haven't developed that technology as far as we want to. So you are likely to see over the next few years passive immunizations or passive immunity where we take, and they'll do this in Ebola cases. So, if somebody who has Ebola, and we know someone who survived Ebola, they'll take and they'll spin out the antibodies from these Ebola patients who survived, and they'll put it into people who are infected and dying with the hopes of getting, that's a last-ditch effort at that point, right? We know that's just like, hey, we've got this weird disease. And if there's a situation that comes up, there will be people whose immune systems can adapt to certain viruses, and that will be used as a tool in the future. I know there's a group down at the University of Nebraska who does that. They do it really quick in hopes that we can make artificial antibodies to some of these emerging. So, a few years ago, Zika came out and it was a big deal. Before that, it was West Nile, and before that, it was, there's all these kind of, there will be another one, right? There will be another. And so we're trying really hard to get to where we can identify these types of passive immunities and get them into, if you're going to die from Ebola, you don't have anything to lose, right? Just, we'll throw the kitchen sink at it, just to hope that you get better.
What's the main difference between better and vaccines, and which one are you?
Great question. I'll cover all that tomorrow, but I'll just give you an idea today. So dead actually means we kill it. It's not going to replicate. Okay? Attenuated means it can still replicate. It's not going to give you the symptoms. So we knock something out, or we passage it until it's not the same virus, and then we put it in. So it has most of the same things, but it's not the same thing. It's not like the flu. It's not going to give you. We passage it until it's not really going to affect you. It'll still replicate, but it's still not going to affect you. The flu vaccine, actually, I don't recall what the flu vaccine is. I'll go look and see. I think I'd know this, considering that I do have a collaborator who does the flu vaccine, but I don't. So there's two proteins that are really important, and the reason I'm not positive on this is because it could be what we call a subunit vaccine. So hemagglutinin. There's two proteins that are really, really important, and they could be subunit vaccines. I'll find that out and answer that question in detail tomorrow when I talk about when I talk about vaccines. So this kind of gives you just a it's more of a cartoon idea of how these things actually, these concepts actually work. Okay. If I'm exposed to an antigen or I do an immunization directly, so if I get a vaccine directly, there's a time period at which, so most of your innate immune system, the first two lines of defense we talked about, are very immediate and real. Like if you phagocytose something, it's happening in real time, right? Adaptive immunity, so innate immunity is very fast and quick, non-specific. Adaptive immunity takes days or weeks. It's not fast, right? So what ends up happening is across time, this is the same thing for a vaccination, right? If I'm going to vaccinate you against flu, smallpox, herpes, whatever it's going to take weeks for that to be effective. Shingles, right? It's going to take weeks for that to be effective. Because what you have is you have native T lymphocytes and B lymphocytes that are going to be exposed, right? We have our T cell or B cell dependent pathway and B cell independent pathway. Both of those are possible. Then we have clonal expansion, right? The antibody producing cells is going to be spitting out antibodies like crazy. That's the peak time. And then we have antigen elimination, right? So the antibodies bind, and then we have our T cells, our CD8 positive TC helper or TC cells that are going to then kill the cells. We get apoptosis, and then we still have some of these cells that stay around. This can be in the weeks to months to years to decades, right? You probably all have experienced this. Every 7 years, you have to get your new tetanus shot. That's because these cells, these surviving memory cells, they kind of fade off over time, right? Why do you have to get a flu shot every year? Because it changes. That's not what happens when you get the tetanus shot. The tetanus shot, what happens is the surviving B cells just kind of fade off, right? They forget what's going on. This goes back to our T cell mediated, independent, and dependent pathways. So B cells are not MHC restricted, so they don't necessarily have to bind to T cells, right? They can bind to any kinds of different molecules independently. Although they will bind at a higher affinity to that T cell, antibodies will, that TCR and that complex, and T cells do have that ability. They'll bind with their epitope at a higher affinity. B cells do not have to be, they don't have to be presented in an MHC complex. So both the ability to present the antigen to a B cell and the ability for a cytotoxic T cell to bind to it are not required in B cells. For T cells to be activated, they do have to be presented in an MHC complex. And that MHC complex will stabilize that antigen. The other thing you're going to find is, this is where the world that I live in, T cells have this is a very linear epitope, meaning there's no secondary structure in that generally, or tertiary structure. These are small antigens because they've been chewed up and spit out by a cell. So they're 10 to 30 amino acids long. They do not have a structure. They bind with high affinity because there's also a complex, an MHC complex there, that's presented to them, but there's no conformation. What's conformation in a protein? What is secondary structure in protein? What are examples of secondary structure? Alpha helices, right? And beta sheets, right? So in a T cell, right, there is no secondary structure, and there's really no tertiary structure. So in a B cell, all these things, right, they bind to lower affinity, 10 to the 9, but there's also the ability to have very conformationally presented epitopes. You think that's good or bad? What did I tell you about good and bad? It depends. Right? Sometimes it's a good thing, right? Sometimes it's a good thing that it can take secondary and tertiary structure. Sometimes this is a better way of doing it. This depends. So different strategies that we can that are associated with activating B cells. Again, one is we talked about this already quite a bit. One is dependent, where the CD4 T cell, which is also a TH cell, can present that, or we can just directly get the antigen presented directly, and then from there, it can. If this is the independent side, from there it can actually go to a plasma and also to a memory cell. And both those are very valid ways of activating it. Antigens are presented to B cells in generally lymph nodes. There are other places, but generally, if a lymph node is a storage house for B cells, okay, and generally small antigens are captured. Right, so we have small antigens, less than 70 kilodaltons. They can be presented. Larger ones are presented by macrophages. And this is kind of the structure of a lymph node, where we have B cells that kind of sit around and they're waiting. And lymph comes in, or blood comes in, interfaces with these, and they come through, and it's going to activate that B cell. Either it's going to present it through a cell, as you see in this situation, where this macrophages come, or this T helper cells coming in and interfacing with this, or it can go directly to them in an independent manner. Or macrophage can present it to it as well. Again, this is like an example where we have these conventional naive B cells are going to come into a germinal center in the lymph node, and we have different outcomes that can occur. We have low affinity. If something binds to low affinity, that cell's going to just die off. Low affinity, what does low affinity mean? We talked about affinity a while back. It's going to, good guess. It's actually, affinity is how strongly it binds, right, at equilibrium, right? So if it's low affinity, it doesn't bind very well, it's going to apoptose. If it has an improved affinity, right, then it's going to go, and this is like a T helper cell here, it's going to then go off and go into a plasma cell, or go into a memory B cell, or it's going to go into an IgM plus, or IgM, we'll talk about this tomorrow. It can form any one of these differentiations. So, and otherwise it can go into, if it's autoreactive, meaning if it's yourself, in theory, if it binds to yourself, then it will go and apoptose as well. This is how the immune system, one of the very, very important properties of the immune system is it does not attack self. Meaning, if I have it, let's say, well, what are some of the immune diseases that you know about? Yeah, rheumatoid arthritis, right? So, what happens is this fails in rheumatoid arthritis, right? It's autoreactive. So there's proteins that are associated with your joints, right? There's proteins and collagen and all kinds of other. I don't know the mechanisms. I'm sure someone does, but I don't know it. Your B cells will actually go and attack those joints. There's a lot of inflammation at those joints. There's antibodies there, and that antibody response is caused because it's autoreactive. Normally, that would be aborted. We would kill that B cell off. But for some reason, whatever it is, there's a reactive oxygen species or any number of other reasons we don't know about that gets continued, and that's a problem. I'm going to give you a very brief primer into antibodies today, and then I will reiterate them tomorrow when we talk about therapeutics that are associated with antibodies. For me, I love this topic, okay? I told you last week some of those topics I wasn't as excited about. For me, I love antibodies. Antibodies are really, really cool in my opinion. So they're composed, I think I talked very briefly, they're composed of 2 subunits there's 2 of each of them. So there's a light chain, right, and a heavy chain. And then there's 2 of each of those. So there's 2 heavy chains and 2 light chains. And they're put together by disulfide bonds. Okay? And there's a constant region. You'll notice that's Cl, CH, that stands for constant light, constant heavy is CH. There's a constant heavy 2 and a constant heavy 3. Right? And there's also glycosylation that occurs in all these different things. So this is a pretty complex molecule, right? And at the end is the variable region. That's where we bind to the antigen. This is also the therapeutic end of all of your drugs. Humira looks like this. Praluent, I'm drawing a blank on all the antibody drugs, but there's dozens of antibody drugs out there, and they all look like this. There's an FC region, that's the constant region, and then there's the FAB. There's 2 FABs per antibody. So this is very reciprocal, right? So you'll find one end here that's the exact same as this in most antibodies. Now, one of the big things in drug development right now is what's called bispecifics. And that's where you take and you make one variable region to one antigen, and you take one to the other. Why would that be cool? Why would we think that would be a good idea?
Saves the phone bodies.
It's fine, keep going. No, this is a mind exercise. You should think about it. Because I'm going to tell you, you will see bispecifics. You're going to, as pharmacists, you will see bispecifics. There's nothing that's approved yet with it, but I'm going to tell you that pharma is on fire about bispecifics. They want to produce a bispecific. Okay, I'm going to give you some ideas. What if I took, one of the biggest problems with antibodies is they get degraded really fast. Well, what if I took and put something on here that made it bound to, let's say, albumin, right? Would stabilize it and make it have a little bit longer half-life, and then I put the therapeutic end here. So I stabilized it, right? And I put it here. Let's say there's 2 epitopes that are important for, so PCSK9 has 2 epitopes that are important to it. One's a trafficking, one's the enzymatic site. What if I made one antibody, that one part of the FAB region, the variable region, that could bind the enzymatic site, and the other that bound the targeting, right? Because then I could block both pathways and maybe have an increased effectiveness. So you're going to start to see this. These are very, very important concepts in drugs, and that's what's going to be this kind of thing. I mean, people who are doing this are very, very smart people, right? So pharma is making these bispecifics, or let's say I make a passive immunization drug to herpes, and I target one glycoprotein on one side, and we designed one we did this at Penn. We made an antibody that bound to 2 different glycoproteins to increase the effectiveness of that antibody, potentially. So there's all kinds of reasons why you might do this. When an antibody binds, there's different pathways it can undergo, right? And that's all dependent upon the effector region. So it can just straight up neutralize. So its function can just be just the block. So I can even take off the effector, right? Sometimes we just put fabs in, and it just blocks, and that's all it needs. This happens very commonly in virus and bacteria, where I just need to block the ability to bind, or to block the ability to fuse, or block the ability to do any number of things, and all of a sudden that's just going to neutralize it. I can also cause what's called an agglutination reaction. So all of my antibodies will cross-react with different, so some of the antibodies are in different forms, and they'll form these big old bodies, these microbial bodies, and those get digested away because they're weird and they're foreign body, and they'll get encapsulated, and that can mitigate the disease. Again, I can also form soluble antigens the same way, and then those get phagocytosed by macrophages, and they get spit out, and then presented back to other B cells that get activated, right? So then we build up on that immune system response. So these get, let's say there's one antibody that's generated against this virus or against this bacteria, they get phagocytosed, they get chewed up, eaten up, and then we're going to present those different antigens. Let's say it's a little bit different. We're going to take those same antigens and present them back to other B cells that may get activated. So the next time it comes through, there might be an entirely new set of antigens or antibodies that target this. And that can be a good thing or a bad thing, right? Because the second time around, we might actually have a low affinity antibody that binds transiently that will block the first antibody. So you can get an infection the first time, your immune system presents it the second time, a different antibody comes and binds and doesn't do as good a job, and then that virus or that bacteria then can come back a second time. You think, oh, we got this problem solved. I've already had shingles, or I've already had chickenpox, and then the next time you get it, it's way worse. That can happen with this kind of situation. Otherwise, I can form a fixed complement, which we talked about earlier, where the antibody binds into the membrane in the foreign cell, and complement will form pores, and you'll get cell lysis. So different antibodies, different types of antibodies can do different things. That's dependent upon what's called the isotype, which we'll talk about in a little bit. B cells mature in the bone marrow. This is why a bone marrow transfusion, if you're familiar with that, is sometimes necessary. So we have these cells. They have, on the outside, they have antibodies, right? They're called BCRs. When they're exposed to antigens, these BCRs change, and they proliferate, they mature, and then they'll start producing mature cells, and then once these mature cells form, and they start they mature. If they're exposed to additional antigens, then they start replicating more and more and more, and they'll start spitting off. And those are selected. Those clones are selected, and then what you end up having is mature cells here, and they'll start spitting off antibodies into your bloodstream and into your lymph, and then those are just circulating. So a lot of you probably have been vaccinated against tetanus. You have mature plasma cells, memory B cells, that are spitting out antibodies to tetanus all the time in your blood. You probably have them against all kinds of different other invaders, including flu and other things like that, other viruses. So both of these guys generate that response. So memory cells are more mature, and these are the memory B cells. They just are constantly presenting. Plasma cells are newer, and but they're the first line. The memory B cells are ones that have been exposed from ancestral cell lines, so they've been exposed before. The humoral response, when you first get day 0, when you're exposed to the first antigen, it takes a little while for it to occur. So you get a primary response to antigen. That takes about 28 days or 4 weeks for it to kind of settle down. So then that's when we generally inoculate a second time. This is why that allows you to form the memory B cells, make it long lasting, because it's the second exposure. This is the reason we generally don't just give one vaccine dose. This is the reason you generally have to go back for a second one. So we're going to come back and we're going to give you a second dose, and that secondary response is even higher, and it generates high titers, and then that generally sticks around longer. So that's generally what we do with antibodies. We'll talk a little bit more about that tomorrow. Again, this is the antibody molecule. They're commonly referred to as immunoglobulins, or IGs, and you'll see IgG, IgA, IgM, and there's different isotypes of that. This is the general structure of all the different classes of, and this is why you see it referred to as a Y molecule. Again, light chains, heavy chains. There's the antigen binding sites, and that's the antigen. Again, we can form all these different ways of responding based on, this is all dependent, all these different ways, which we talked about, precipitation, agglutinization, neutralization, inflammation, complement, is all dependent upon the Fc region of the molecule. And that Fc region determines that the sequence of that determines what isotype it is. So all these mechanisms go to isotype, which I'm going to skip ahead here, and there's different classes and subclasses. Tomorrow I'll get into subclasses. Today I'll introduce the concept of classes to you. And the reason this is important is because when we make therapeutics out of antibodies, the isotype is very, very important to how these therapeutics respond. Okay, and as pharmaceutical scientists, not only do we have different immunoglobulin isotypes or classes that we use, we also will take this molecule and we'll do all kinds of things with it. Tomorrow I'll introduce you to 25 different constructs that are all related to immunoglobulins. There's SPABs, SCFB, FBs, bicycles, all kinds of different nanobodies. There's all different kinds of these constructs that are all associated with immunoglobulins. So we'll take and put different constructs in there to get different effects. Now, each one of these, IgMs is the first response to an antigen. You'll notice that it forms a pentamer. So there's actually 5 of them in a star formation. Right? IgGs are very singular. IgAs, they're secreted from mucous membranes, right? So you see these all around the mucous membranes. They're a dimer. They form dimers. That's all related to the Fc region. IgGs, they they're B cell activators, and they don't cross placentas. IgEs, this is the one that causes your extreme inflammation and your allergic responses. So they're very, very important in that. Your primary B cell response is commonly an IgM. IgMs have lower affinities. Now this is a lot more realistic of a diagram. These molecules here look a lot more realistic. So you're going to see all different kinds of conformations and structures of this. I'll go into detail on these tomorrow. Talk about how they affect drug delivery and just drugs in general. But generally, you're going to see an IgG response. Then you're going to go into more of an you're going to see an IgM response, and then you're going to go into an IgG. Almost all future after the first round are IgGs, and all of your therapeutics almost exclusively are IgG subclasses. So, and this all happens. This can have this. This happens 6 to 10 days after you get an IgM response. So this recombination event occurs. It's called a somatic hypermutation, where it's actually going to take the variable region and it's going to switch the effector region or the Fc region, and it's going to make it 6 to 10 days post inoculation. It's going to make it a permanent IgG. So we can also do affinity maturation or somatic hypermutation. So these, it's kind of crazy. Your immune system can change and improve the antibodies it's making through affinity maturation or somatic hypermutation. We try to do that as well, right? We have artificial antibody machines, constructs, bacterial libraries, yeast libraries, phage libraries, and we try to go through these artificially. We'll just artificially mutate stuff, and your body does the same thing. And it adds random mutations in order to get better binding, and if it does get better binding, those B cells are saved, those clones are selected, and then we get memory. We also can get future antibody waves and isotype switching from that. So we go from an IgM to an IgG. Are you getting how complicated this is? Because I haven't even started talking about really complicated stuff that happens with these. The genetics behind this are insane. I'm going to spend a little bit of time talking about FC functions today, but really the major part of it will come tomorrow. And I completely understand that this is complicated and ridiculously crazy, but this is the future of drugs. Okay, and this is the reason I get excited about it, is because when we make drugs, this is the future of vaccines too. And those are the things that you're going to see, right? That you will see in 10 to 20 years another reinvigoration of small molecules, but almost all drugs now are antibody-based. All new, a large chunk of the drugs, new drugs are antibody-based. Isotyping is all dependent upon the FC region, the type of FC region. The FC that you see, the FC region will dictate the structure. I told you structure equals function 100 times. Here's another case where it's true. This effector region will dictate whether it's a dimer, monomer, or a pentamer, right? It also dictates where it goes, right? So different, like macrophages have different FC receptors than eosinophils. So you're going to get a different response, you're going to get different phagocytosis. You can go into complement, you can go into opsonization, you can go into just straight up neutralization, all based on the effector. So the FC dictates how your immune system is going to respond, right? And the variable region will dictate what it binds to. So when we have a naive B cell, it's just floating around, it hasn't been bound. It's a short-lived B cell, only 4 to 7 days. It can get activated, and then it'll go into a memory B cell, and it generally, once it gets exposed again, it will generate very, very high affinity antibodies. It's long-lived in the animal. So a native B cell is the first one you're going to see that's been exposed to the antigen, and then we're going to switch to memory B cells after it's been exposed a second time. Here's kind of some examples. So neutralization, if I generate antibodies against PP120, which is one of the proteins on the HIV works with, or the HIV utilizes as a fusion protein. If we generate antibodies against it, one of the problems is CD4 on their T cell can't recognize it, and so it has trouble. Hemagglutinin on influenza, it can't recognize because of glycoproteins. I think we talked about this, the glycan shield we talked about when we talked about carbohydrates. Same thing with tetanus shot, right? That results in muscle contraction because some of the effector functions are not, if you get a different antibody response from that, you can get a problem with neutralization on that one as well. We can also affect this man-made by generating things against, neurotoxins like cobra venom and enzyme phospholipases, and we can also generate antibodies for blood clotting inhibitors. So all these things can be mediated, and effector function is how they are taken and cleared by the body. Again, they also can form antibody complexes, and then you can have them cleared by macrophages. Macrophages commonly generate these, will clear out these complexes, the antibody-antigen complexes, which are commonly very complex because you have bivalent antibodies. It binds in 2 different places. Opsonization is the technical term for how an antibody initiates phagocytosis in an innate immune cell. So if you have an adaptive immune response that binds these antibodies, this is not to scale, right? These antibodies are not as big as that. If you actually believe this, that bacteria would be as large as this antibody, which is completely not true. This bacteria is orders of magnitude bigger than the antibody. For the extent of this is what we call PowerPoint science, right? So this antibody binds multiple times. We have a macrophage here. It's going to bind to the Fc gamma receptor. That's going to opsonicize or phagocytose that, and that increases the ability of detection, and then that also clears that response out of the body. So you go from an adaptive immune system back into the innate immune system. So these two Fc gamma R1 and Fc gamma R are both very responsive. Those are IgGs or IgAs. Those are very, very responsive to phagocytosis. And different effectors will cause different responses to that. So, and then some will form complement. There's a complement receptor in there. So there's different effector systems can cause different responses. As we mentioned earlier, complement not only initiates inflammation, but what else does complement do? Forms pores, right? It'll form what's called a membrane attack complex, and it will allow that to be killed off. And that's mediated by, again, starting with the adaptive immune system. It directs the formation of the membrane attack complex and will lyse things like bacteria and tumor cells. We also have what's called ADCC, which is antibody-dependent cell-mediated cytotoxicity, and basically this is initiated by natural killer cells, and it leads to apoptosis of different. And the important part of this topic is not that you memorize all these different, right? The important part is that you recognize that different antibodies with different FCs will allow your immune system to go down different pathways, and different hosts will initiate different ways of dealing with it. Okay, now that I've sit and talked to you for almost 2 hours about this, right? What are some of the takeaways from this lecture? First and foremost, your immune system is outrageously complex, right? First takeaway, okay? So when they say things like, I'm going to say that vaccines are bad, right? That's a vastly oversimplification of what's going on in your system. Okay? Just recognize that. Like, no scientist out there thinks that vaccines are perfect. We recognize the net effect is positive, right? It saves people's lives. It saves people from morbidity, like being sick. Okay? We do recognize that because the immune system is so complex, it's not a perfect entity. There's no way you can predict what the immune system is going to do. Your first lesson today is the immune system is outrageously complex. And if something goes wrong, it can be very, very problematic. Second lesson today is the immune system is neither good nor bad. Right? I haven't talked to you, I'll probably mention it tomorrow. I haven't talked to you about the bad things that happen because of it. Right? We live in a different era than has ever existed for humanity in many regards. And one of the side effects that we have not thought about, but that impact us every single day, is that our immune system is not designed to live in a modern environment. It's just not. The food we eat, the environment in here, it's very sterile in here. There's very few pathogens in this room, right? In comparison to if I went just out in the wilderness, right? I'm not exposed to ticks or mosquitoes or, I can cook my food, right? I don't have to worry about what's in the ground. This environment is completely sterile. What I eat is drastically different than what I ate even 100 years ago. Is that a good or a bad thing? It's both, right? So there are consequences, right? Right? I have high cholesterol because it's a bad thing. But at the same time, I'm now able to live to be 80 years old because I have a cheap supply of food. Right? It's neither a good nor a bad thing. You have to take it on par and just go, okay, how can I improve what I have, the situation I'm in? Drugs, the third thing I want you to know out of this, is that most of your drugs, a lot of your diseases, are influenced by your immune system. The second you realize that because of the complexity and because of everything else that's going on, right, you should be able to make better decisions about what you're giving to people, right? Antibiotics, right? It's good to know about antibiotics. How does that, we haven't talked about antibody-based antibiotics, right? Is that a new class that's emerging? Yes, it is. There are new antibiotics. How does your immune system deal with the bacterial infection? Why can't your immune system fight all bacteria? Right? It's a good question. Right? Because the immune system should win. Right? I told you how it works. But guess what? Bacteria and viruses and all these things, they fight back. Right? It's not a simple like, hey, I got you. Antibiotics kill bacteria, but guess what? That bacteria is going to fight back, right? It's going to find ways of dealing with that, and it's going to find ways of surviving. There is no simple drug that's going to solve all our problems. In fact, cancer has the same resistance mechanism. Cancers have the same resistance mechanisms as bacteria and viruses, so they will develop resistance to chemotherapeutics, just like a bacteria will develop a resistance to penicillin. Cancer will develop resistance to Taxol-based drugs. They can pump them out. They can do all kinds of different things. So when we talk about this and we do talk about the immune system, this is a war that we're constantly fighting. All of this happens in the lymphatic system. It's the most, I shouldn't say all of it. A large chunk of it happens in the lymphatic system, and we don't mention that at all. We talk about blood, right? But lymph is also circulated throughout your body, just like blood is. It's circulating around all the time. At the intersections of blood and lymph systems is where these germinal centers and lymph nodes are, and this is where a lot of your humoral immunity from B cells and antibodies occurs. This is where the fight is waged, is in the lymphatic system. And this is where we go basically to B cell maturity and to T cell maturity is at these intersections, because T cells will bring in antigens to that site and B cells will respond at that site. Okay. I'm not going to start autoimmunity today. We'll leave that for tomorrow. Tomorrow is another very exciting day. When you get to be my age, right, different things excite you. I'll just say that.